Hello and welcome to Lecture 1, starting with our new unit on kinetics and energy of reactions. In this unit, what we are going to do is we're going to explain how collision theory can be used to understand how chemical reactions occur. We're also going to look at some of the different variables that affect how fast reactions occur. So this is new. We haven't talked about the speed of reactions before. We've just talked about how the atoms are rearranged. But now we're going to talk about the speed at which that happens and what types of things play a role in that. So some new words for this unit. We're talking about something called kinetics. And kinetics, let's get the pen here. Kinetics involves talking about the speed of a chemical reaction. And the speed of a chemical reaction is actually called the reaction rate. Now, there is a numerical thing that you could do to calculate the speed, but we're not going to be calculating speed in first year chemistry. We're just going to be talking about relative speed. So is it fast, like the striking of a match, or is it really slow, like maybe the rusting of these nuts and bolts? And the other thing that we will briefly touch on is, well, why are some things really fast and why are some things really slow? Well, it has to do with the way the reactions occur. They occur differently. They occur by different pathways, and those pathways are called reaction mechanisms. So when we talk about the mechanism of a reaction, we're really kind of talking about the pathway that it takes in order to get to where it's going. So the reaction mechanism is actually the pathway. I keep losing my pen here, guys. So it's the pathway that reaction takes. In some reactions, their pathway is really straightforward. Maybe the compounds collide and they form a new singular compound. But in other cases, the pathway can be much more convoluted. So for example, this one here, you don't have to know the details of this reaction, but you can see that if I've got NH3 and O2, these are doing something else entirely because now I have nitrogen monoxide and water. So this one must occur in steps. Okay, now in AP, you would talk about all the different steps, but we're not going to talk about the steps now, but you should know that there are steps. And those steps involve having to break bonds and then make brand new bonds. And so you can't do these things simultaneously. So you have to have some breaking of bonds, and then you have to have the making or the formation of new bonds. And that gives us the ability to take something like NH3 and oxygen and make something brand new like nitrogen monoxide and water. And all of those little baby steps along the way, the breaking these up and making them into these and forming the new ones, these are called the elementary steps. And we can't see them individually, but we do know that they affect things like the speed of a reaction. So that's what a reaction mechanism is. It's like the pathway that it takes to get there. Some are very short and sweet, and some are much longer and more drawn out. Now, how do we get the reaction to happen with all of those steps? Well, there's this thing called the collision theory, and a collision theory helps to explain how reactions occur, like what actually causes them to occur, because we know that just because compounds run into each other doesn't necessarily mean that they react, right? If they did, that would be bad. It would mean that your car could burst into flames when it rained. It would mean that your clothes might melt when you run them in the washing machine, or the fact that you're even wearing them could be a problem, right? So how come some things react and other things don't? Well, a reaction takes place when there are what are called effective collisions. So what on earth is an effective collision? Well, effective collisions have to have these three things. You have to have the compounds or the elements physically touch. So they have to collide, but more than just that. They actually have to collide with enough energy, okay, and the correct orientation so that they can stick, if you will, and start to create products. So that's what you're seeing here in this image. These guys are hitting, but they're not in the right orientation, or maybe they're not hitting hard enough, right? If they hit hard enough and they hit with the correct orientation, you start to get a reaction. So if you meet all of these criteria, you're actually touching with enough energy and correct orientation. What you have is an effective collision. And effective collisions are the key to actually having a reaction take place. If they're not effective, they just bounce off of each other and nothing happens. Some things do this really well, and the reactions are really fast. And some things do this not as well, and so the reactions are much slower or less effective, less efficient. So what we're going to do now is we're going to just kind of go through the different factors that affect how fast reactions occur. And again, all of these are going to be very conceptual. They're not going to be mathematical. We're just going to go through a bunch of ideas and think about how these ideas can be used to explain what we witness. So chemical reactions occur because particles collide with each other. Okay. And then how quickly that reaction occurs depends on how many of the collisions occur and how effective those collisions are. And when we look at how many collisions and how effective they are, we're brought to the speed of the reaction rate. So anything that speeds up the rate of collisions will also help speed up the rate of the reaction. So we're going to go through the 5 big things that can affect the rate of the reaction. The first one is just the nature of the reactants, right? What phase are they in? What kind of intermolecular forces do they have? What kind of bonds do they have? So there's a lot of things at play. We're going to focus on 2 things in particular, which is the type of bonds. But remember that chemical reactions involve the breaking and forming of bonds. Okay. So for this reason, we're going to focus on bonds. Bond type makes a difference. Now, we learned earlier that ionic bonds are relatively easy to break. Especially when they're in their aqueous form, right? Ionic compounds dissolve really easy. Water rips them right apart. So because of that, ionic bonds are easier to break, and the reactions of compounds that have ionic bonds tend to occur pretty fast. They occur pretty quickly. Compare that to covalent reactions. Covalent reactions tend to occur more slowly, because they're more difficult to break and therefore they require more energy. And so it's just a more involved process. So when we say the nature of the reactants, that's what we're talking about. In particular for us, we're talking about the type of bonds that occur. So again, relying on past knowledge, ionic bonds occur between metals and nonmetals, or possibly contain polyatomics. Covalent bonds occur between nonmetals only. So you should be able to look at a reaction and tell what kind of bonds are in the compounds, and then you have some idea about whether or not it's going to be a relatively fast or a relatively slow reaction. Another thing that can make a difference is, I think I went too far, the concentration of the reactions. Got 2 slides out of order. I'll fix this before class, but here we go. So number 2 is the concentration. And so the question in your notes is, well, which one has a higher rate of collisions? A parking lot with 10 cars or a parking lot with 100 cars? Well, that's what concentration kind of is. Concentration is how much stuff is in your solution. So here we've got 2 different pictures. Low concentration without a lot of compounds in it, and higher concentration with a lot more. So you can think of them kind of like cars in a parking lot. As the concentration of the reactant increases, right, the number of collisions will also increase. So you can see they're going to run into each other more often. And what that means is that the reaction rate is going to increase as well. And now here's where you have to be careful. If the rate is going faster, then the time is going to also be faster, which means the time it takes for the reaction to occur decreases. So the rate is going much faster, so the reaction time goes down because it's happening faster. Now, concentration only applies to gases and mixtures, and that's because solids and liquids, they have huge numbers of fixed concentrations that don't really change. So this is only applying to gases and mixtures really means, in our case, homogeneous mixtures, which are aqueous solutions. So what about gases? How does this play a role in gases? That was the out of order slide here. Let me go back. So here for gases, they're not in aqueous solution, but if you take a gas, an increase in pressure for gases is just like increasing the concentration, and that's because think back to what we learned about gas laws, right? If we increase the pressure, it means we decrease the volume. Those are inversely related. So as we squish the gas down into a smaller space, we haven't actually changed the number of particles, but they are now crowded, right? So they're crowded more, so they're going to run into each other more often. So the molecules are being pushed closer together, which causes more collisions, which is going to make the rate faster. Right, so there's the slide we already did. So number 3 is temperature. Temperature can also affect the rate of reaction. So again, I'm kind of using cars as an example in your notes. Which one would have a higher rate of collision? If you had a bunch of cars traveling along together at 30 miles an hour, or if you had a bunch flying down the road at 100 miles per hour, right? When you talk about temperature, what you're really talking about is an increase in kinetic energy. And kinetic energy is the energy of motion. So if you have increased temperature, you have faster molecules. So this directly affects the speed of the colliding particles. An increase in temperature will cause more collisions, and a higher percentage of those collisions will be effective collisions because they're going to hit with a lot of energy, enough to really knock them into each other and allow them to form that kind of middle of the road, getting ready to react compound. We'll learn about what that is later. But here what we have, more energy, right, which means moving faster because they're at a higher temperature, means more effective collisions, which means my reaction rate is going to go up. This is why we heat things up sometimes in lab, right? Because we're trying to get it to go faster. A lot of reactions will happen very, very slowly on their own, but we don't have days and days and days to wait. So by pushing them into each other more often, by turning up the temperature, we can make the reaction go faster. Number 4 has to do with surface area. The more surface area that is exposed, the more of the particles can actually run into each other and have effective collisions. Right? So this means that more particles are physically able to touch each other. And let's talk for a second about how we get more surface area. Man, this has got a typo on it too. This is the same as the previous slide. I've already started recording. I'm 15 minutes in, so I'm not going to restart the thing. But here we've got some surface area differences. Okay. If I have a big solid chunk of something, right, the only place that the reaction can occur is where the two different things can come in contact with each other. So I've got all of this real estate on the inside, right, that cannot even begin to react because it's hidden, right? It's stuck on the inside. So if I take that big lump of whatever that compound is and I grind it up and I turn it into a powder, right, then I can have that same lump, right, but now it's got all of this extra surface area, right? Even though it's the same amount of substance, it's got a lot more opportunity to run in to the different particles of the other compound. So by taking something and increasing its surface area, and the way that we increase the surface area, right, is we grind it up or pulverize it even. We can increase the surface area by magnitudes, and by doing that, we can cause the reaction to occur much, much faster. Okay. So increasing the surface area, more effective collisions, reaction time is going to go up. And I'm sorry, reaction rate is going to go up and reaction time is going to go down. Man, I'm having a hard time with this first show, guys. I'll do better next time, I promise. And then the last one is number 5, which is the presence of a catalyst. Now, a catalyst does not actually change the reaction. Remember that we learned in our previous unit that if we had a catalyst, whatever it was, it could be light, it could be energy, it could be an enzyme, whatever it is, we're going to write it up here. And the reason that we write it up here is that they don't actually change the reaction. They don't change the A plus B, and they don't change it into something different than AB as the product. But what it does do is it speeds up the reaction by changing one or more of the steps in the overall mechanism. It's like finding a shortcut when you're taking a road trip, right? It doesn't change your starting point and it doesn't change your arrival, but it changes the path that you take to get there. So generally what it does is it lowers this thing called activation energy, which is the energy that is required to make a reaction go. We're going to learn about activation energy in the coming lectures, but it's going to lower that threshold of energy needed. So maybe it doesn't have to be as hot. Maybe the collisions don't have to be as hard, but it allows the reaction to proceed at a faster rate than it would be able to if that catalyst or that helper wasn't there. And again, they're not consumed by the reaction. So wherever they are up here, they stay up there. And this was the picture. I was trying to come up with a picture of what a catalyst does that wasn't super technical. And I found this. I thought it was really funny because I grew up with bulldogs. And here the catalyst is the skateboard, right? You can use a skateboard to get to school, or you can use a skateboard to get to the store, and it's going to be faster than just walking, right? You don't consume the skateboard, you don't eat the skateboard, you don't use it up and it's no longer there for you to use, but it does help you get there faster. It changes the pathway of how you get there, it changes the mechanism. Instead of walking, now you're rolling. So those are the 5 things that will speed up a reaction. Now here's what you need to do, whether you're at school or at home. You have 2 things to complete now. The first thing is summarize the ways to speed up a reaction in that space that's there in your notes. Use your own words. And then the second thing is when you go into Google Classroom, you will notice something different this week, which is there are 2 assignments that have the blue number 1 in front of them. You need to do them both. I couldn't get them to combine because of how they're assigned. For each one of them, you'll be taken to CK12. You'll have a short reviews, a couple of video clips. One of them is actually pretty entertaining. And then there are review questions or practice questions for you to obtain mastery. You'll need to get 10 correct in order to reach your mastery goal. So that's what you need to do now, and then I'll see you in the next lecture.